Welcome to this session. This is secondary physics tips. The topic today we are learning about pressure, and we'll be taking you through. My name is John K. Dongo. Welcome, and I hope we shall learn something together. What is pressure? So, what daily activities involve the use of pressure? So, think around that. What you do every day, and what involves the use of pressure, and then. Could pressure be useful to us, and in what ways could it be useful to us? Without pressure, how could life be difficult to us also? And do we have negative effects of pressure? That is also another pertinent question. And which ones do we know? So those are just questions to brainstorm and to introduce our lesson. And here are some few tips about pressures, natural pressures of objects that we know around, and we have extracted this from university physics. Yeah, so you can see the center of the sun has a pressure of 2 times 10 raised to 16. It is really big. Then center of the earth has about 4 times 10 raised to 11. The highest sustained laboratory pressure is of the order of 10 raised to 10. That is still very, very large. Deepest ocean trench at the bottom of it, that is pressure exerted by water overlying it, of the order of 10 raised to 8. And then the spike hills on a dance floor, yeah, so these of the order of 1 million pascals. Automobile tire, less than 1 million. Atmospheric pressure at sea level, it's a very it's less than 1 million pascals. Normal blood pressure is about 1.6 times 10 raised to 4. Then the best laboratory vacuum that has very little pressure has a 10 raised to negative 12. That is very, very, very low pressure. So these are just some of the pressures, and this is in excess of the atmospheric pressure. All the ones labeled with a superscript A. Then the ones labeled with superscript B, like normal blood systolic pressure, uh, is equivalent to 120 torr. So that torr is another unit of measuring pressure. Yeah, so it's just let's make some reflection. Uh, this the first diagram A, and there's the second diagram B here. What can you see in the first diagram? Uh, it's that there are two pictures of 2 feet. Try to look at the difference between the two and try to relate that to pressure. So there are two shoes with different designs, and it's like the two people are walking on a muddy path. So the reflection here is that uh, walking on a muddy path in perhaps a flat or slightly raised shoes could exert some pressure on the ground. But now, if you have ever walked on a muddy path, maybe in flat shoes or slightly raised shoes, you must have noticed that you made some dips. But if you were in highly heeled shoes, as in the first picture, where let me try to seek my arrow, yes, as in this picture, then the dips would perhaps have been deeper. Now, why is that so? And assuming that you are the same person, or the two people walking in different the different shoes have the same weight. Then in the second diagram here, there are two guys here trying to drive in some objects into some wall, some wooden wall or something like that. You can notice that the two are exerting different amounts of energy. If you look at the first person is saying ouch, and the second is saying yes. So there is a difference. It's like one of the object is getting in very easily, and the other one is getting in not very easily. So the reflection here is that it is easier to drive. Is it easier to drive a blunt object or a sharp object into a wooden wall? Which one requires greater force to drive in? Between A and B, so give reasons for your answers. Ultimately, driving A requires more energy because it has quite some large surface area as compared to the second object in B, part B. Yeah, same case to the first illustration here is that the two people exert different amounts of pressure, and that is determined by solely by the surface area of the heel. So the observations that we can make from those reflections, those diagrams, are that pressure depends on the area of the object acted upon by a force. And now the second one, how does pressure relate with the area, surface area of that object? Is that it increases with when the area reduces. That gives an inverse relationship. And thirdly, that pressure increases with increase in force. This is a direct relationship between pressure and force. So there's an illustration here, small illustration to explain this, that when the surface area is very small, that is, we are assuming this triangle is resting with this tip, uh, uh, resting on this tip such that this is now the surface area uh, that is carrying this triangle. So if we take its weight to be equal to its force, then the pressure exerted on this small surface area becomes very high. So that is that. In the second illustration, we are now inverting this triangle such that now we have a large surface area, and therefore we expect that there will be very low pressure according to this statement acting on the weight of this triangle. So what we can infer is that pressure is inversely proportional to area and directly proportional. So what is pressure? Uh, we can now conclude pressure to be a ratio of the force acting on an object to the area of the surface on which the force acts. What we are trying to say is that pressure equals to force over area, and to illustrate that, if a force is acting on an area given by the diagram here, then the pressure should be given as force divided by area. But now the force depends on the direction or the angle between the line of action of the force and the plane of the area. So because force is a vector quantity, we say that maximum force should be equal to the vector of force, then multiplied by sine 90, because sine 90 is the maximum ratio of sine theta, which should give us 1. So that now the vector of force should be equal to the maximum force acting on the object or on the area. So the maximum force is when it is directed at 90 degrees. That one we have already said. So the maximum pressure, for maximum pressure, force has to be at right angles with the surface. Uh, being at right angles means that it makes an angle of 90 degrees or is said to be normal to the surface, or what we can call perpendicular to the surface. So we are now narrowing down, and we are close to coming up with a concrete the definition for pressure, and that is from the illustrations, and we can conclude that pressure equals to force over area, and we say that maximum force F is the same as or force at 90 degrees to the surface should be the same as F sine 90, and sine 90 is equals to 1 because equals to 1 because 90 degrees is the same as normal or perpendicular. So we can conclude that pressure is equal to the force acting at 90 degrees or normally per unit area. So that is the concrete definition of force, of pressure, sorry, that pressure is the force acting normally per unit area. So good. Let's see how we can apply this in a case scenario that we want to discover how pressure is affected by surface area. Pressure exerted by a body is affected by surface area. If we increase the surface area, how does pressure change? So we are giving a case scenario where we are saying that there is a concrete rectangular prism that is producing different magnitudes of pressure depending on the surface area or the face on which its weight acts. So for a rectangular prism, we know it have different faces that have different dimensions or surface areas, and therefore if we allow it to lie on different orientations, we expect to have different values of pressure. So we are to calculate the pressure exerted by the block when standing on its smallest face and also on its largest face. So we are giving a hint to take mass of the block to be 10 kilograms. Sorry. So and then we shall discover something. So this is the orientation when standing on the smallest face. We are assuming that the dimension 20 centimeters by 10 centimeter at the bottom part here make I don't know where my cursor has gone. Yes, this face, which is the same as this face here, uh, will make the smallest face, and a certain amount of pressure will be exerted by the weight of this block when standing at this point. And when we also invert it to lie down such that the largest face now becomes our surface area or cross-sectional area, then we expect a different value of pressure altogether. So we are assuming that these two arrows, the two arrows are facing the surface areas, these bottoms here. So that's the assignment, and try to calculate now the pressure using the formula that we've already got up there, so that we can be able to see the difference in pressures. So now let's see the solution. So the first thing we shall do is to calculate the force acting on the blocks. Uh, the force is equal to mass times acceleration due to gravity. Remember the mass was 10 kilograms. Then acceleration due to gravity is taken to be roughly 9.8, or we can round off that to 10 newtons per kilogram. That gives us 100 newtons for the force. And then we calculate the areas of the smallest and largest faces simultaneously, respectively. So starting with the smallest, we call it minimum area or A min. We convert the values. 20 centimeters should be equal to 0.2 meters times 0.1 meters for 10 centimeters. And this is because we want to calculate the pressure in pascals. Remember, pascal should also be equal to newtons per square meters, so not square centimeters. That's why we have converted that. The maximum area should be 0.5 times 0.2 to get 0.1. So these are the two phases. Therefore, we expect that pressure maximum should coincide with area minimum, and that should give us get us to the third point where we calculate the pressure exerted on the smallest phase, then the largest phase. So pressure exerted over to the smallest phase by the smallest phase exerted when the body is lying on its smallest phase, we call it P max because it's now the maximum pressure. It's equal to force divided by the minimum area. We said that pressure is inversely proportional to area. That's why P max corresponds to A mean. And we get 5 times 10 raised to 3 newtons per square meters, which is the same as 5 kilopascals. The minimum pressure, that is pressure exerted when the body is lying on its largest phase, is given as by 1 times 10 raised to 3 newtons per square meter, or 1 kilopascals. So you can notice the difference between the two, that having the body to stand on its smallest phase exerts a pressure of 5 kilopascals, and just twisting it to lie on its largest phase reduces the pressure to 1 kilopascal. So that's the difference. So there is an effect of the cross-section area or surface area on the pressure produced, or that a body exerts on a certain surface. So there is a difference, and we have noted, or we have explored mathematically that, and we've discovered that increasing the surface area or cross-sectional area reduces the pressure exerted by the body. So let's go to get to us to some other task here. We are going to do some analysis of the same body, but now we have a graph here instead of having the calculating, instead of calculating the pressure will be given here, and then we shall infer, or we shall be able to get the surface area having been given the force and the pressure. So for instance, from this graph, if we are given a force of 40 newtons, then we ask the minimum pressure and the maximum pressure that the body can produce. Then we are supposed to just come here, the 40 at 40 newtons. Then being at 40 here, we can travel along a horizontal line, and where our horizontal line coincides with our red line, we drop it down and read the value. The value should be something less than 0.5 newtons, and for the second one we can see it's around some 2 newtons here. So that's part of the analysis. That's one. We can be able to get the pressure when exerted by the force when the body is lying on its largest phase. That's represented by the blue line, and then the second one, when it's lying on its smallest phase, it's represented by the red line. So let's see the case that we're supposed to analyze. If we assume that the size of the block is constant, we keep it constant, then we vary the amount of force acting on the smallest and largest surfaces, then we can deduce from the graph the relationship between the force applied and the pressure produced. So to deduce that, first of all, check the nature of the lines. So the force is changing linearly with the pressure because the lines first of all are straight, and then the rate of change of force to pressure is different for the two lines. So that means that the surface area is different, but there should be a direct relationship between force and the pressure applied. Or we can take the equation for pressure equals to force divided by area. Then we try to write the equation for defining these two straight lines here. So the first one, we know that we have varied force against pressure. So on the y-axis we should have force, or the way y-intercept should be force. Therefore, if we write the equation in terms of y equals to mx plus c, the equation of a straight line, then we expect that pressure to have an equation that describes the relationship between force and pressure. So essentially take the equation pressure equals to force over area, then make force to be the subject of the formula, then write it in the form y is equals to mx plus c. That will give the equation or the relationship. Secondly, we can look at or deduce the smallest surface area and the largest surface area by assigning. We can do that by either looking at the two straight lines. We assign them which one has the largest surface area and which one has the smallest surface area. So which one will give us the bigger gradient? Because if you write the equation as the equation in terms of force as the subject of the formula, you will find that the equation will give you the area, sorry, the area to be represented by the slope of these two lines. So which one has a slope, a larger slope? That is so because the larger the slope, we expect the larger the surface area, and the smaller the slope, then the smaller the surface area. And essentially the red line should give us higher gradient because the line is steeper. It has a larger slope. We expect it to have a larger slope, and therefore we expect it to have a larger surface area. And as we said, that surface area corresponds to uh, an inverse relationship with the pressure, then we should be correct if we say that the red line has a larger surface area because it has smaller pressure. It has smaller pressure values. As we had said, even taking the same amounts of force gives smaller pressure in the red line and larger pressure in the blue line. But take time. You can pause this video and take two suitable points. Try to take to calculate the gradient for the two lines, and from the gradient you can be able to know which line has essentially larger surface area and which one has smaller surface area, and try to see whether the values or the results will be consistent to the equation that we had discussed in slide 5. So that equation on slide 5 is giving us the hint. You can pause this video and or go back and see that equation if you've forgotten that pressure. It was pressure equals to force over area. Then try to rearrange that equation to fit the equation describing these two straight lines. So that is that, and I'm very happy for today because we've looked at something very important, and I hope you've got something. You know now what pressure is. It is a ratio of force against area, and it is essentially defined as the force acting normally per unit area or force acting perpendicularly per unit area. So we go back to the topic of pressure, and I'm expecting to do a video on pressure of fluids, that is liquids and gases. Please keep checking for more videos, and subscribe to this channel, the Science Tips channel, so that you may be able to see next video. And you can also recommend some of the videos, topics that you'd like us to do tutorials on, because we are committed to making sure that you get every tip in science at your fingertips. Thank you very much. Enjoy your learning. Thank you very much.